Okay, so today we're going to look at basically rules of exponents, but how we apply those to polynomial expressions. So we have to review some of our exponential notation, i.e., review how we designate powers and things like that, and then remind ourselves, what those things mean, so that we can combine things raised to powers. Right? We've done it before with numbers. Now we're going to do it with letters and such. So just a quick reminder that whenever we see anything raised to a power, it just means that that thing is being multiplied that many times. So b to the n just means you have n number of those b's. So if you had, x to the fourth, you literally have four x's being multiplied together. That's all that means. So something like this, right? We know that this is simply just 6 times 6. This is negative 1/2 times negative 1/2 times negative 1/2, which of course would still be negative, right? Because there's three of them. That these two would cancel, but the third one would make it negative again. You'd have negative 1/8. And then this would be, of course, 0.8 times 0.8 times 0.8 times 0.8. You just have to figure out what that is in your calculator, because nobody knows what that is in their head. So raising things to powers, or showing something with an exponent, is really just shorthand. It's an idea of, instead of writing out a big long string of numbers, we can put something to a power. Well, we need to remind ourselves that when something is raised to a power, only that specific thing is being raised to a power. So this right here, this first one, is really -1 times 5 to the fourth. The negative is not being raised to power, just the 5, right? So this is -1 times, then you have 5, 5, 5, 5, right? You multiply these together and get 25 to 25 is, I don't know, some big-ass number, but it would be negative whatever that number is. Whereas here, I think it's 625. Let's do 625. If we do this one, now that the parentheses are here, now the negative is getting raised to that power of 4, and now it's -5 times -5 times -5 times -5. And the negatives will all cancel, right? Because a pair here goes away, a pair here goes away, and then you get positive 625. So you can see that there's a huge difference by slapping those parentheses on there, just like these two will be the same thing. As far as they act differently, right? This is -0.2 times -0.2 times -0.2, whereas this one is -1 times 0.2 times 0.2 times 0.2. But because it's an odd power, it means the same darn thing, right? Because when you have three of them, these cancel, but then the third one keeps it negative. So these two are actually going to be equivalent, right? They're going to have the same answer, even though algebraically they're technically done two different ways. So that also reminds us that if a negative number is raised to an even power, it's always positive, and if a negative number is raised to an odd power, it's always negative. A couple other examples, and remind us that we can evaluate these things by simply plugging in numbers for our variables, which reminds us again that a variable is simply just an empty vessel that we can pour something into it. And normally we pour numbers into them. So you can think of it as an empty box, and we just haven't quite yet opened it to figure out what's inside that empty box, right? It's a crappy Christmas present. You unwrap it and go, oh, yay, I got a 2 or a -3, right? So again, you have to remember that just a is being squared here. So this is 5 times 2, right? If we put in a 2 squared, which is 5 times 4, which is 20, which is totally different from this one, which is 5 times 2 quantity squared, which is 10 squared, which is 100, right? So you can see big differences. Just like on this one, only b is raised to a power, so it's 5 times 2 times -3 squared. You'll notice I have parentheses here because b is being squared, so all of b is being squared. If we let b equal -3, then -3 is being squared. And so that gives us 10 times 9, or 90. right? The negative goes away because the entire thing, all of b is getting squared, and the negative 3 is inside b, right? That box is getting squared, and inside that box is negative 3. So it's everything inside the box times everything inside the box. So it's negative 3 times negative 3. Just like here, we would have negative 3 plus 2. That whole thing is being squared, which of course reduces to negative 1 being squared, which is just 1. So in addition to all this, we have to remind ourselves of the order of operations, right? Please excuse my dear Aunt Sally, that old fun thing where you got to do what's inside the parentheses first, then you got to raise it to a power. Okay, what about when we're doing a multiplication and division with powers? Well, we just have to remember the simple rule that when you multiply, your powers add, and when you divide, your powers subtract. And really, sure, you can have those memorized, but it really comes down to just like a no-duh thing, right? If I have x cubed times x to the 4th, well, remember, that's just 3 x's from the first one, and 1, 2, 3, 4 more from this one. Look how many I have. I have 7 of them, right? So it's not like this is some sort of magic. It just comes from the basic principles of what it means to raise something to a power. It just means you have that many things, and I have that many more things. And when I multiply them together, I have a big-ass string of that many things. Division comes from the same idea. So if we have x to the 6th over, let's say, x to the 4th, well, that's just 1, 2, 3, 4, 5, 6 of them on top, and 1, 2, 3, 4 of them down below. And we know that we can always reduce when we have a fraction with multiplication like this. And we're left with just 2 of them on top. 6 minus 4. Again, it's not magic. It just comes from the idea of what it means to have something raised to a power. I have m many of them on top. I have n many of them on the bottom. The n many of them will all cancel out, and I'll be left with the difference, m minus n. All right, so here's a simple example, right? 3 of them, 4 of them. It's going to just give me 7 of them, 3 of them, 4 of them, right? Doesn't matter if it's a number or a letter. Same rules apply, right? 6 over 4. It's just going to be 2 of them. And again, it doesn't matter if it's numbers or letters. The same rules apply, which reminds us of another thing. When we're dealing with letters, the rules still apply. Whatever we can do with numbers, we can do with letters. And more importantly, whatever we cannot do with numbers, we can also not do with letters. Oftentimes when students are learning algebra, as soon as you throw a letter in front of them, they seem to think all the rules of mathematics go out the window, and now that it's letters, I can do whatever I want with them. No, 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 no. Remember, again, the letter is just an empty box, and you're going to put a number inside it, and because you're going to put a number inside it, that box can only do the same crap that the number can do, right? So rules of addition and subtraction and multiplication and division, all those things still apply to letters because they are really just numbers in disguise. Okay, let's take it a step further, and we know that if we put these two together on the top, we're going to have 9 of them. That's a Z. And then we have the 3 on the bottom that we can subtract away, and we're just going to be left with 6 of them. Same thing here, right? We've got 7 on top. Down at the bottom, we've got 2. Remember, this is a 1. There's a little invisible 1 here, so we really have 3 of them on the bottom, which leaves us with 4 when we're done. Another simple example, when we've got multiple variables, you can combine the p's and you can combine the q's just like you can combine the constants, right? So you're going to have negative 3 times 2 gives you negative 6. You're going to have p squared times p, which is going to give you p cubed. And then you're going to have q to the 4th times q to the 5th, which is just going to give you q to the 9th. Same thing here, right? 16 divides by 4. That's just 4. W to the 9th over W to the 8th, right? There's just a difference of 1 of them. And then Z cubed over Z leaves me with 2 of them. And then finally, applications of these things. If we want to find the amount in account after 8 years, if the initial investment is $7,000 invested at 2.2% interest compounded annually, well, you have to know what annual interest what that formula is, right? So your amount equals principal times 1 plus r over n to the ny. That's the generic formula for compound interest, where P is your starting principal, A is the amount you have. It's like your future value. It's the amount that you have in your account after so much time. R is your interest rate, always as a decimal. N is the number of compounds you have per year in both places, and then Y is the number of years. So in the case of this, we started with 7,000. 1 plus 0.0225. And because it's being compounded annually, we're only doing one compound per year. So this is a 1. And then, of course, this is a 1. And then we do it for 8 years. So it really just simplifies to 7,000 times 1 plus 0.0225 raised to the 8. And then, of course, 1 plus that, this just becomes 7,000 times 1.0225 to the 8th. And then, of course, you would slap that in your calculator, right? Do 1.0225 to the 8th, get that number, multiply it by 7,000, and there you go. There's your answer. All right, so that's all I have for you in this lesson.